Hi everyone and welcome to a new video about noise analysis, and this is our example number 3. In this example I will discuss the noise analysis of a RC circuit. And of course we will look at the calculations step by step, and we will verify these calculations using simulations in SPICE. So let's look at our example. What we have is the following situation given. We have the following circuit RC, and in this case we have the capacitor value given of 1 nanofarads, and we have 3 cases for our resistor. We have the 1 kilo ohms, 10 and 100 kilo ohms. So we will look at it in more detail step by step for each case. And if you look at the circuit here, and you know that also from AC circuit analysis, this circuit is a low pass filter. So we measure the output across the capacitor, and we have the input voltage here given, and it will be applied to this RC circuit. So for really low frequencies, the input voltage will be passed approximately with the unity gain at the output. But if you have a really large frequencies, the attenuation will be of course a lot, so you will have almost nothing in the output as a signal. And also as a noise, so that's actually one of the important things of filtering. This is of course a low pass filter. So in this case, for each resistor value, we would like to calculate the following issues. We would like to have the output noise voltage spectral density, which is given here by the small letter E and out, and the input noise voltage spectral density, the total RMS output noise voltage, which is of course then given in RMS values, and we would like to have the signal to noise ratio SNR. So actually we have now 4 situations, and we will do that for each case step by step. So let's look at our solutions. So how do we work this out? Of course, we will begin with the model, and for that we need to disable the independent source. And in this case we just have one. We have only the voltage source, so we know that from circuit analysis the voltage source will be a short, and a current source will be of course an open. So independent voltage source will be a short, so I will short it out. That's actually what I have. Now, as a summary again, thermal noise power spectral density is given by this expression, which is then the square of the noise voltage spectral density, which is then here 4kTr, which is then given here the units volts squared per hertz. And noise voltage spectral density is the square root of this expression, and that is then given by this expression, which is then given by the square root of the 4kTr. In this case, for this circuit, the thermal noise voltage spectral density at the output in general is given by this expression. And what you see here, what you recognize is that this expression, it has the same, of course, the E sub n and E sub n. It is the thermal noise voltage spectral density, but this expression shows that it is independent of the resistor value. So it's very interesting, and it will be of course also proved in calculation, also in the simulations. So what I of course want to know is what is all these parameters are. So the K is in this case the Boltzmann's constant, so it's just a constant. It has a value of 1.38 times 10 to the power minus 23, approximately of course, joules per Kelvin. The T is the absolute temperature, so it is given in Kelvin. So for room temperature operation, let's say 27 degrees, we will have approximately for the T 300 Kelvin. So I will also use this in my calculations. The R's are equivalent resistance, so resistor value in ohms seen at the node. So if you look at this node, for example, or this node, it depends. You will have your resistor value, and your capacitor will be then the C, and it must be in units of farad. But let's look to the noise in an RC circuit in more detail, because we would like to of course understand why this is the case, and why don't we have the resistor value R, which was of course the case in a pure resistive circuit in the previous 2 examples. So a reactive component, it doesn't matter if it is a capacitor or an inductor, on its own will not produce any noise. So that is in ideal case the situation. Of course, a real capacitor or a real inductor will always have some shunt or series resistor, so you will always have some noise, even if you have just one capacitor or one inductor. The interesting thing is, if you combine your resistor, so it is when combined the capacitor with a resistor or an inductor with a resistor, the thermal noise does not depend on the value of the resistance, which is very interesting. And why that happens is the following. Let's go through this step by step. A larger value for a resistor, so if you have a really large value, so if you increase this, you will generate, of course, more noise. So let's say you have 1 kilo ohm of a resistor, and if you make that 10 kilo ohm, you know from this formula that will, of course, generate then more noise. That is very straightforward from this formula. But what we also know is if you make your resistance larger, it will reduce your bandwidth of your circuit, in this case, in a low-pass filter. So we know that 1 over RC, which is then given, of course, as the omega, the cutoff frequency, will be then smaller when you increase your R, or of course increase your C, it doesn't matter. But let's set this capacitor C constant, and if you just make this larger, you will have also a reduction in your bandwidth. That's very interesting. So you reduce your bandwidth, but you will increase your noise. That is interesting. That means the following: both effects in noise and bandwidth will cancel each other out, and we will see why that happens. If I now look at the signal bandwidth again, as I said before, then in hertz will be then 1 over 2 pi RC for this circuit, which is just first order low pass filter. And if you go from the signal bandwidth to the noise bandwidth, you need to make a conversion from this in hertz to, again in hertz, but then in noise bandwidth. And that will be then this expression times pi over 2. Now, I won't go through details. You can, of course, work out the integral, but that will be happening for first order system. Then you will have 1 over 4 RC. Then the RMS noise voltage, of course, in the RMS values, will be then given, of course, in this form. So this is then the capital letter E sub n is then the small letter e sub n times the square root of that noise bandwidth, and that will be, of course, have a value of volts RMS. This is, of course, what we already know from this expression, and this is what we have here. So if I now substitute the values for my RMS noise voltage, I have then the square root of the 4 kTr times the square root of 1 over 4 times RC. Now, just a very simplified form here. I will place this in the numerator in the square root, so I will then get rid of the square root here. I will have this simplified form. Now you can already see that you can simplify this even further. You can get rid of this two 4's, and also I can cancel out these r's in the numerator and the denominator. So I will have then this expression, which is then the square root of k times t over c, which is then, of course, now in RMS value. So it's interesting. I don't see any resistor here. I don't see any bandwidth here, so it is all independent of the bandwidth and also independent of the resistor value, which is really interesting. That's only caused by an effect of an RC circuit. That means the following: if you have a terminal noise voltage spectral density for the circuit, which is then given here as a unit volts per root hertz, it is also in the RMS value exactly the same, because it is independent also of the bandwidth or the noise bandwidth. But we'll see that, of course, and we will prove this also in our calculation, also in simulation in SPICE. So let's look at our next step. First one is the input noise voltage spectral density. We know that the capacitor on its own doesn't produce any noise. We already said that. And the input noise voltage spectral density will be then only caused by the resistor. So the expression for the terminal noise voltage spectral density of a resistor is then given by this expression. We know that already. So it's just specifically the resistor. So the square root of the 4 kTr. And if I now look at the terminal noise voltage spectral density of the resistor for each case, that can be then shown below. But if I know that I look at the input, which is of course not the output, I have already just only the effect of the resistor. So that's only caused by the resistor, which actually is already said here. So then the input noise voltage spectral density in this case is the terminal noise generated by your resistor only. So I can say, let's start with the resistor of 1 kilo ohm. I can use this formula for my terminal noise spectral density, and I just substitute the values, and also for the resistor 1000 ohms, I will have this value for my input noise spectral density, which is then 4.071 nanovolts per root hertz. If I move on for 10 kilo ohm, I have this expression. I have then 12.88 nanovolts per root hertz. And if I do it for 100 kilo ohm, I have then a similar expression. Then of course substitute for this resistor 100,000 ohms, and I have then 40.71 nanovolts per root hertz. Now summarizing these in the table, I have this. You can see if I increase my resistor by a factor of 100, the thermal noise voltage spectral density of that resistor will be then 10 times increase, because that is the square root of that R, that's the action. So if you increase your resistor, you will increase your thermal noise spectral density by a factor of 10. So let's also look at the output noise spectral density. This is for the input. Let's also look at the output. Output noise spectral density will then only depend on temperature and also the capacitor. We already said that, and of course we use the value for the temperature 300 kelvins, and the capacitor was given as 1 nanofarad. The output noise voltage spectral density is the same for the resistor values 1, 10, 100 kilo ohms. We already said that. Why? Because we can use then this expression, and we don't see any resistor in this expression. So it doesn't matter if you have a 1 mega ohms here or 1 giga ohm or 1 ohms, it still will give you this result. So what we have, just substitute the values for the Boltzmann's constant, the temperature, and also the given 1 nanofarads, you will have 2.035 microvolts per root hertz. That's what we have now. So we have the input noise spectral density and also the output noise spectral density. Let's move on to the total RMS output noise voltage spectral density. I mean the total RMS output noise voltage, which is the capital E ends out. This is actually the next step. We know the total RMS output noise voltage is independent of the operating frequency and also the bandwidth. It doesn't matter if you have an operating frequency or the bandwidth. And it is the same for all resistor values, so it is independent of the resistor, which is of course very interesting, but it is the case for an RC circuit. Now, in this case, since this is of course not per root hertz, but it is a volts in RMS, we can just use again this formula and then substitute the values. We will have 2.035 microvolts RMS. So that will be the case for each resistor value. What you also have is the next question, which was the final one, the signal to noise ratio SNR. So the SNR, in summary again, is a measure that compares the desired signal level to the noise level. So there is the ratio between these two. So this is desired, of course, that is what we want, and noise level is of course what we don't want. So we would like to know what the ratio of that is, but in signal power and also noise power. So there's a ratio actually in powers, not in voltages and not in currents, and that is expressed in dBs. Now there is a ratio, of course, larger than 1. It can be happening. Then it means actually that you have in dB more than 0 dB, and it indicates that you have more signal than noise. But if you have more noise than signal, then you have actually a ratio which is then between 0 and 1, for example 0.5. Then you will have a value as a dB which is then negative. That will actually indicate that you have more noise than signal, which is of course not what we want. We will like to have more signal than noise, and we will actually want to increase our SNR level. Okay, for this circuit, in this case, the SNR at the output for a specific frequency can be calculated using this formula. And the interesting thing is, we already have that in a 20 log form, so we will already give it in the units of decibels, so in dBs. And you can see this expression at the output, of course, is only that total RMS output noise voltage. So if I substitute the value here, what I have in this, I will have 113.8 dB, approximately 114 dB, and that will be the case for each resistor. So it only depends actually on the capacitor. So the SNR is the same for each resistor value, and I can now make the summary in a table. For each resistor value I have exact same total RMS noise voltage and also exact same SNR at the output, which is then 130.8 dBs. Now what are the conclusions? The conclusions are the following. The SNR is independent of the resistor value, already said, because I already seen it here. We can also see it here. And we also say that the E and out, which is then the total RMS noise voltage, will increase if you decrease your capacitor. So if you decrease your capacitor, make it smaller, for example 10 to the power minus 12, so 1 picofarad for example, this will increase because you will then divide it by a small value, and of course you will increase your RMS noise voltage. By increasing actually your capacitor, you will then increase your SNR value. So if you want to increase your SNR level or filter out more noise, you will actually require a larger capacitor. That's actually one of the conclusions here. Okay, let's look at the simulation results, and we start with the input noise voltage spectral density, and we will see what we have. So this is actually what we have. This is the circle we had, the R and the capacitor of 1 nanovarads. What you see here is actually the following. This is the plot, actually the line for the case where you have a resistor of 100 kilo ohms. So you can see it is 40.71 nanovolts per root hertz. You can see it also in this plot. So this is the y-axis, which is then the input noise voltage spectral density. This is the frequency in hertz. And this is for the resistor of 10 kilo ohms, and it's done for 1 kilo ohm. So we can see that these values do match very well, actually exactly according to my calculations, with the simulation here. So that is a really nice result. So you can see that it will just increase by increasing your resistor value, and it will stay constant, so it is really independent of the frequency. Let's also look at our frequency response, in this case looking at the bandwidth, and we will make a Bode plot of our RC circuit. And this is the RC circuit we have, and this is the Bode diagram, specifically just the gain, and we have for 3 cases the plots. You can see the cutoff frequency actually for each resistor value. So if I make the summary here, the cutoff frequency is given of course in hertz 1/2 pi RC. And if you just make your capacitor 1 nanovarads, and for each case you can have the calculation for each cutoff frequency. So it will be for 1 kilo ohms will be 159.2 kilohertz, which will be actually seen here. So it has actually the largest bandwidth. If you go to 10 kilohertz, you will actually decrease your bandwidth by a factor of 10. And if you go to 100 kilo ohm, you will have 1.592 kilohertz. So actually approximately 1.6 kilohertz. You can also see it from here. So this is the blue line, which is then the case for RS 100 kilo ohms. The green line is for 10 kilo ohms, and the dark red line will be for the 1 kilo ohm. Now let's look at the next steps. Will be then the output noise voltage spectral density. You can see the following here. It starts actually where we have for each resistor our input noise spectral density. So this was the input noise spectral density when you have a resistor of 100 kilo ohms, and it was the resistor input noise spectral density where you have the resistor value of 10 kilo ohms, and this for the 1 kilo ohms. But you can see it will decrease and then approach actually 0. That will also the case for this green line and also dark red line, due to that cutoff frequency effect of the low pass filter. So in summary again, you can see this is then for the input thermal noise voltage, of course, density. And you can see for each resistor value, and this is actually, if you look at 100 kilo ohm again, you can see it starts at 40.71 nanovolts per root hertz. You can also see that here, but it will decrease and go all the way to 0 due to that low pass filter action of this RC circuit. And the cutoff frequencies again here shown as an effect of this plot. So for each resistor value you can see the cutoff frequencies, and if you increase your resistor you have a very small cutoff frequency, and if you decrease your resistor you have a very large cutoff frequency or bandwidth. So that's actually also seen from this output noise spectral density. Now let's also look at the total RMS output noise voltage, which is then shown here, and this is a really interesting plot because now we have this circuit again, and we have now the total RMS output noise for each case of our resistor, so 1 kilo ohms, 10 kilo and 100 kilo ohm. What you see is actually the curve, the blue line and then the green and the dark red line, will of course start a little bit different and with a different slope, but it will approach the same output noise voltage. So integrated, you will have here in this case 2.036 micro volts RMS. And that's actually one of the issues we already discussed. It is not dependent on the resistor value, because this one is for 100 kilo ohms and this is for 10 kilo ohms and this is for 1 kilo ohm. But it is independent. If you look at it doesn't matter actually what the resistor value is, because your integrated output noise voltage, RMS voltage, will be the same. So again, total RMS output noise voltage is independent of the resistor value. And it only depends on this one. We already calculated this and we had 2.035 microvolts RMS, and I have here in my simulation 2.036, which is pretty close. Yeah, I think this is just the rounding of errors. Okay, let's also look at the noise to signal, so signal to noise ratio, SNR. In this case, what you see is that the following, again, the plot for 3 resistor values. What you see is they start all at very low frequency, let's say DC, very low high, because we have then a very low frequency and most of the signal will be passed, so you have a very large signal to noise ratio. But at some point, of course, they will start to decrease, and which is interesting is, for these 3 lines again, that the minimum SNR level for each line, for all of these 3 lines, will be at approximately 113.83 dBs. We had calculated, actually, in our calculation, we had 113.8 dBs using this, and is approximately exact the same again, due to that rounding of errors. But we have the minimum SNR is for all resistors exact the same. So again, the SNR level, signal to noise ratio level, will not be dependent on the resistor, just the capacitor. That's actually the major operator here that will define your output noise voltage, RMS, and also your signal to noise ratio, not the resistor. And you have seen this also here. And that's actually the case in this plot, and we have now 3 plots. Of course, how they start and how they propagate, of course, as a frequency will of course differ, but in the integrated form you will have a SNR minimum level which is exact same for all of these 3 cases for our resistors. So again, in summary, these are the resistor values, these are the total RMS output noise voltages, and these are the SNR values. And we have very close to what we have in our simulations. So that's what we have now for our example, and you can see that this is very interesting, where you have a RC circuit that the resistor value is completely out of the picture, and the major contributor, or actually the only contributor in this case, is the capacitor, when you of course just keep the temperature constant. Of course, if you change the temperature, that will also have effect, but it will always have an effect no matter what kind of circuit you have. Now I will jump to the simulations in SPICE and also show you there what you can see also in SPICE. So let's jump to SPICE now. So we are in our SPICE simulator, and you can see I have generated already my resistor and a capacitor, so RC circuit here, and with my input voltage, which is of course an AC. It doesn't really matter what kind of source it is. Of course it must be AC, so frequency dependent, but you can take anything what you want. So it can be a cosine, it can be a square root of a triangle, but just what you prefer. So I just take something and press OK. This here R has an asterisk here, so it is actually a control object. So I will select the control object here, and I will then select several values here. So you can see that I made a list for 3 cases. So parameter 1 is 1K, parameter 2 is 10K, and parameter 3 is 100K, which is actually the values for my resistor. I can of course add a new one, so I can make 1 mega, and it will be of course added. So I have then 3 cases, but of course I just want, 4 cases, but in this case I just want of course 3 cases, so just press OK. That's why we have actually an asterisk here. And this is of course the capacitor value, which is just 1 nanofarad. And this is the output where I measure the noise, and this is the input voltage, and now we'll generate the noise plot. So I go to analysis, as I did also in the previous examples, go to noise analysis, and then select your start frequency and your end frequency. This is the number of points to make it accurate, and I found out that this is actually the maximum what you can get in this SPICE simulator. You can of course plot just one generate one plot, for example, the total noise, which is then the RMS output noise voltage. You can also have the signal to noise ratio, input noise voltage spectral density, and also the output noise voltage spectral density. So I will do all of them, all four of them, and you can see what we have. So let's generate this. It will calculate it, and we have the plots here. Let's see what we get. It will take some time. Okay. Okay, now this is the output noise spectral density. So you can see it is, I can also make a label here and make it a little bit larger. You can see actually this, the V out means actually that is then for the first case. It's actually this one. So if I make it red, you can see it's for the 1K, and you can see it has the largest bandwidth. And then you can also see if I make the label, so I can delete this. If I label this, this is actually where it's all constant, and then make a label again and make this larger, again 20. You can see that it is at 1K. I will just label this again. It is 4.07 nanovolts per root third, of course. That's actually also what we had, and this is now 12.87, so it's almost 88 nanovolts per root hertz, so it's also really close to what we have calculated, and this is now for the 100 kilo ohms. So again, you can see the plot for different resistor values. Okay, let's also look at the input noise voltage spectral density, and the interesting thing is here that it is just constant for frequency for different cases, so it stays constant. Of course, I can make this a little bit easier to see, so I will make the lower limit at 0 and upper limit, let's say 50 nanos, and then go in 6 steps, and you have then this, and I can now again make a label, so I can then see that also the values for each resistor value, and then make this a little bit larger. You can see the V out for this one, for example, V out for 100 kilo ohms, it is 40.71 nanovolts, and in this case, of course, is the input noise voltage spectral density. Again, for the 10 kilo ohms and 1 kilo ohms, you can see it is all in agreement with our calculations. But you can also see it just stays at the constant level. It will not change as a frequency, as a function of the frequency. Okay, let's also look at the total noise. And again, you can see, I will also make a label here. You can see here, it will just stay at that value. And I will also show you that in the label. So let's also make this larger. And for each case, you can see, for example, if I now go for this one, which is then for the 100 kilo ohms or 10 kilo ohms, you can see it is highlighted now in red. And also in this case, it is now for the 1 kilo ohm. It all have the same total output noise voltage, which is then in RMS. So it is integrated for very large frequencies. Okay, now the signal to noise ratio, again, as I said before, it will start, of course, very large because the frequency is very low. That means you have almost all past signal, so you have a very large signal noise ratio. But if you filter out a lot, you will have some minimum value, which is then around here. And if I now look at, for example, again to my labels, label generate legend here, again make it larger, you can see it will have exact same value because this is the Y value for my SNR. So if I highlight this, which is then for the 1 kilo ohms, you can see it is the same value as the 10 kilo ohms highlighted here, and also for the 100 kilo ohm. So again, we have proved also in our simulation that it is very close to what we have calculated for the input noise voltage spectral density, the output noise voltage spectral density, the total RMS voltage noise at the output, and also the signal to noise ratio. And this is interesting for our RC circuit because in a filtered circuit you can see that in this case, for the simple first order RC circuit, that only the capacitor is the main contributor for our output noise. Of course, if you keep your temperature constant at 300 Kelvin. So the resistor values will not have effect on the output noise voltage, and also not the signal to noise ratio if you look at it for after some frequency. Alright, this is for example number 3, specifically for the RC circuit. I will continue with different examples using active or passive circuits, so keep in touch, and if you have any questions or comments about this example, please let me know and I will try to answer them as soon as possible. Thanks again, and see you next time. Take care.